Hello, and welcome to Astronomy 100. In this segment, we're going to continue our discussion about the seasons. And keep in mind that in the prior segment, before this one, we were talking about all of the observed phenomenon that you could see if you were to go outside and look at the sun on a regular basis. And then we're going to tie all these ideas together to a complete understanding of why the Earth experiences the seasons. So let's pick up where we left off. The third thing about the sun that you would observe if you had the chance to go out on a regular basis is that if you were to notice the sun as it moved across the sky, you would notice that the sun's path that it takes across the sky is different throughout the year. So this is sort of a top-down view. This is sometimes in astronomy what we call the dome of the sky view, the perspective of us looking down, being above the sky. There's somebody standing out in the middle of the wilderness here, and we have the cardinal points on the horizon. We have north, and we have south, and then we have east, and then we have west. And what I want you to notice is that these yellow lines are indicating the path that the sun takes across the sky throughout the year. So let's start with this one here on June 21st. On the day of the summer solstice, remember, the sun is going to rise north of east. It's going to make this journey across the sky that is going to end up having the highest altitude that it's going to have for the entire year, not quite hitting the zenith. And then, of course, it's going to set north of west. This is the point of view from some latitude in the United States. It could be the latitude of San Diego, or it could be somewhere else that is sort of mid-latitude United States. Rising north of east, hitting the point not quite straight overhead, and then setting north of west. Now, on the day of the winter solstice, the sun is going to rise south of east, and where it hits the meridian is going to be at a fairly low altitude. Remember, the lowest altitude for the year. And then when it hits the horizon, when it sets, the sun is going to set south of west. So rising south of east, making a very short journey across the sky, and setting south of west. Now, on the day of either equinox, you notice that both dates are listed here. This could be the vernal equinox, this could be the autumnal equinox. The sun is going to rise due east. It's going to take this journey across the sky where it doesn't quite hit the points of either one. It's going to be somewhere in between. And the altitude when it crosses the meridian is going to be the one that you see here, in between the lowest and the highest. And then when it sets due west, it of course is going to complete this journey across the sky. So each day of the year, the sun rises in different places along the horizon. It hits the meridian at different altitudes, and of course that forces the sun to either take a very short journey or short path across the sky, or a very long journey or long path across the sky, and it's going to change on a daily basis. The fourth observation, I'm going to use the same picture, and this one involves the notion of time. If you were to go outside and if you were to time how long it takes the sun to make that journey across the sky, let's say that when the sun rises, you take a stopwatch, you click go, and then you just simply wait out the hours for the sun to cross the sky until the sun sets, where you click stop. What you will be calculating is what we call the length of daylight. This simply means how long of time, how long the sun is out for daylight. And then of course there's a length of night, which is how long it takes for the sun to come back around to the next sunrise. Now, if you did this throughout the year, what you would notice is that on the day of the summer solstice, the sun is going to have the longest period of daylight for the entire year. And I'm going to quote you some numbers, and the numbers I'm going to quote you are for San Diego, and these numbers are approximate. But on the day of the summer solstice in San Diego, we have the sunrise, and the sun is actually out for about 14 hours until it sets. Now remember, it has to be a 24-hour day, so that means the sun is going to be down or below the horizon for about 10 hours. So we have a 10-hour night, and we have a 14-hour day. Now on the day of the winter solstice, when the sun rises, we end up with just the opposite. We have about a 10-hour period of daylight, and then of course that means we have to have a 14-hour period of night. So we have a 10-hour day and a 14-hour night. On the day of either equinox, when the sun rises due east, and sets due west, we have 12 hours of daylight and 12 hours of darkness. So a 12-hour day and a 12-hour night. And that is actually what the word equinox means. Equinox means equal night. Equinox, equal night. And you have 12 hours of daylight and 12 hours of darkness on either the vernal equinox or the autumnal equinox. So the length of daylight compared to the length of night is going to change as each day goes by. The longest day of the year is on the day of the summer solstice. Shortest day of the year is on the winter solstice. Now, the next observation has to do with the shape of the orbit of the Earth itself. And in this illustration here, I want to show you that we have the Earth in its orbit around the Sun, and the pieces that go with this are really two-part. The first part is, I want you to notice how the orbit of the Earth is not a perfect circle. The shape of the Earth's orbit around the Sun is what we call elliptical. So this is the shape in mathematics called an ellipse. The Earth's orbit is elliptical in its shape. And then I want you to notice how the Sun is not at the center. So the Sun is actually off-center from what we would imagine would be the middle. So the two things together, the Earth's orbit is elliptical and the Sun is not at the center. Now, there are some terms that go with this, and I'm going to introduce these terms, and I'm going to put them up on the screen one by one, so follow them very carefully as we do so. Whenever a planet is closer to the Sun and then of course further away from the Sun, it presents 2 points in the orbit that can then be named based on the proximity, or how close to the Sun or how far from the Sun the planet is. So let's introduce the ideas. Before we give the individuals, let's sort of show the actual distance when it comes to the Earth and the Sun. The distance between the Earth and the Sun, we give that a name in astronomy, and it's actually a very important name. It's an important distance. We call it the astronomical unit. The astronomical unit, by definition, is the average distance between the Earth and the Sun. Now think for a moment why we would have to say the average distance. If you look at the screen, you'll notice that sometimes the Earth is closer, sometimes the Earth is further away. So there is no one particular distance that the Earth is always at. It's always either a little closer or a little further. So we call it the average of the two, or the average distance between the Earth and the Sun. And again, that is called the astronomical unit. And in case you want to know, it is 93 million miles, which is that average distance. When the Earth is closest to the Sun in its orbit, we call that perihelion. And it comes from the word Helios, who was the Greek god of the sun. So perihelion translates to closest to the Sun. And when the Earth is furthest from the Sun, this is called aphelion. Notice that the pH is not the traditional F sound, it is aphelion. So the Earth reaches a point called aphelion, and the Earth reaches a point called perihelion. And even though we're using the Earth in our example here, this is also the case for any object that orbits the Sun. So every planet in our solar system that has an elliptical orbit has a perihelion point and an aphelion point as well. Let's put in some numbers. When the Earth is at its perihelion point, it is 91.5 million miles from the Sun. When the Earth is at its aphelion point, it is 94.5 million miles from the Sun. And obviously the average of these two works out to be 93 million miles. And most people, when they see this, they think that this is, of course, a very logical thing when it comes to the concept of the seasons. So listen very carefully, because what I'm going to do is tell you how this very obvious thing on the screen here turns out to lead people to the wrong conclusion. If you are slightly closer to some source of heat or some source of energy, you would expect it would be hotter. If you are further away from a source of heat or source of energy, you would expect it to be cooler. So in this example, it is very tempting to say that when the Earth is closest to the Sun, that it is the season of summer. And when the Earth is farthest from the Sun, that this should be the season of winter. It just makes logical sense. But I'm going to show you one more piece of evidence that would seem to run contrary to this, which of course poses a bit of a problem. When we are closest to the Sun, it actually occurs in early January. And if you think about it, at least in the Northern Hemisphere, in early January, we are right in the middle of the season of winter. So during winter in the Northern Hemisphere, we are actually closest to the Sun. Now that doesn't seem to make sense. Why would it be winter if we're closest to the sun? The other part of this is when we are farthest from the sun, that occurs the first week of July. In the northern hemisphere, we are experiencing summer. So the Earth is actually furthest away from the sun during the season of summer in the northern hemisphere, and it is actually closest to the sun during the season of winter in the northern hemisphere. Now, this is a major problem if your explanation for the seasons are that the distance between the Earth and the sun is the cause for hot summers and cold winters. In reality, it is not. There is no connection between the distance between the Earth and the sun and summer versus winter. So if all your life to this point you have believed that this is the cause for the changing seasons, you need to stop believing that, because that is actually not the reason why we have seasons. Let me show you a couple more things that will kind of hopefully drive this point home. This picture on the screen that you see right now of the elliptical orbit has been exaggerated. The point is to exaggerate it to show you the shape of the ellipse so that it's easy for you to see and understand. What I'm going to show you is an accurate representation. So this is now an accurate portrayal of the orbit of the Earth around the sun. And most people, when they would look at this, if they didn't really know any better, they would probably say that this is a circle. It kind of looks like a perfect circle. But in reality, this is actually an ellipse. If we measured this distance from here to here, and then we measured this distance from here to here, they are not equal. So it is a little bit smaller this way and a little bit further or longer this way. It is truly an ellipse, but just barely an ellipse. So the shape of the Earth's orbit is elliptical, but not by much. And you'll also notice the sun is actually not at the center. The little white X or the white cross is where the center is. Notice the sun is slightly off center. So there is truly a point where we are closer to the sun, and there is truly a point that we are further from the sun. But here's what I want you to think about. Look at how very, very close to a perfect circle this is. And if you think about the seasons, especially in different places around the world, the cold winter days and the hot summer days are dramatically different. One example I like to quote is Las Vegas. If you've ever been to Las Vegas and lived there for any lengthy period of time, you'll notice it's very, very hot in the summertime, but it actually snows in the wintertime. So you can't have these extraordinarily different temperatures between hot summers and cold winters if the distance between the two is just ever so slightly different. So it can't necessarily be this closer to the sun and further from the sun difference to make the dramatic temperature changes. Now, one final thought. One common mistake that people make is the myth we're going to bust in today's segment. We're going to call it our today's Mythbuster, shall we say. Many people mistakenly think that the sun gives us its heat, but in reality, the sun cannot give us its heat. The reason why is when heat transfers from one place to another, it has to have material or a medium to travel through. Heat can travel through air, heat can travel through water, heat can travel through solids. But space is a vacuum, and there is no way for the sun's heat to transfer to the Earth. So the concept of being closer to the sun, making it hotter, and further from the sun, making it cooler, doesn't make sense. In reality, the sun doesn't give us its heat, the sun gives us its light. The light from the sun can travel through the vacuum of space, and when that light reaches the surface of the Earth, it will cause the Earth to heat up by having light shine on it. But the sun cannot give us its heat, so being closer or further away is not going to make any difference. What is the actual reason why we experience seasons? Turns out it has to do with the fact that the Earth is tilted on its axis. And you'll notice in this illustration down here is these dashed lines would be perfectly straight up and down, but the Earth actually has a 23.5 degree tilt from being perfectly perpendicular to its orbital plane. And so if the Earth orbited around the sun, being perfectly perpendicular to that, we would not have seasons. But in reality, it is tilted by 23.5 degrees. In the next segment, we're going to see how this 23.5 degree tilt of the Earth on its axis is the sole cause for the hot summers and the cold winters. But we're just about out of time, so I hope you'll join me then.